In this video, we'll learn about graph convolution for chemicals. Understanding the properties of molecules is a very important topic in the field of chemical science. For example, here's a molecule called acetophenone. This molecule is used to make polymers that are typically used as resins. In order to make polymers with this molecule, understanding its properties such as melting point, boiling point, solubility, the heat of formation, and entropy are very important. For this molecule, we know these properties from previous experiments, but what if we want to determine these properties for many unknown molecules? Performing many experiments to determine these properties would be very costly and time-consuming. Can we teach a machine learning model to rapidly predict these properties? The answer is yes. There is a mathematical concept called graph theory. In graph theory, we describe an object as the combination of vertices and edges. One example is the social network from a platform such as Facebook. Here, vertices represent individuals and the edges represent the connection between individuals. With this graph, we can use graph theory methods to determine, for example, the shortest path between the two individuals or the number of overlapping friends. Advanced techniques can be used to determine more interesting properties, such as the influence of an individual. Other examples include the highway and subway system. We can use methods of graph theory to find an optimal path between two locations. The navigation apps use these techniques to guide us to our destinations, which we use every day. The graph theory can also be applied to molecules, which is called molecular graph theory. In molecular graph theory, vertices represent atoms. For example, acetophenone has 1 oxygen, 8 carbon, and 8 hydrogen atoms. To keep track of specific atoms, we're going to number each of these atoms. Edges represent, as you might have guessed, the bonding between atoms. Acetophenone has 1 CO bond, 8 CC bonds, and 8 CH bonds. To keep track of the edges, we use the index of the two atoms connected by the edge. Each vertex and edge have features associated with it. Here we will represent them as VI for vertices and EIJ for edges. For vertices, or atoms, there are several well-known ways to featurize. The element of the atom is obvious, but we can also add features such as hybridization degree, number of hydrogen neighbors, and so on. For example, this oxygen atom is sp2 hybridized and has a degree of 1 as it is connected to 1 carbon. It does not have any hydrogen neighbors, it is not aromatic, it is not in a ring, and also does not have a formal charge. Typically, we use the one-hot encoding method and integer to represent these features. And these features are then concatenated to make a feature vector for this specific oxygen atom. Similarly, we can featurize the edge using the bond properties. What kind of bond is it? Is the bond conjugated? Does it have a stereochemistry? Or is it a part of a ring? We also typically represent them using the one-hot encoding method and integers. The graph theory is especially handy when we're trying to teach a machine learning model. For example, we want to encode the atom feature using a neural network. To do so, we would use the edge connectivity to pull the neighbor's feature and apply them to a neural network. For example, V3 has 3 bonds and 3 neighboring atoms. So we will pull this information and apply it to a neural network named FV. The form of FV is important and decides the performance of the model. And one example is shown below. Here, these circled plus indicate the concatenation. So we are concatenating the two vertices associated with an edge. And we multiply it by weight WV and add bias BV. We can perform activation to the resulting vector represented by sigma. Since there are multiple bonds, we usually divide by the number of bonds. And this is a simple way to encode the atom feature. The advanced graph convolution model uses a different type of FV and also could involve different types of pooling and so on. We call this function graph convolution as it is based on graphs. This process is convolution because the function FV is applied multiple times to all atoms in a molecule. For example, we can apply it to the oxygen atom or the tertiary carbon atom. Similarly, we can also encode the edge information. Here we would encode an edge by pulling the features of connected vertices. An example of the edge convolution function involves concatenating the edge and vertex features, followed by linear multiplication and activation. Once again, scientists are working on developing a better convolution function to improve the accuracy of the model. Another example would be a convolution of the CC bound edge. So that's the graph convolution. We can take in the graph information and perform a few graph convolutions, followed by pulling up the vertices and edge features. The pooled features are then applied to a neural network to describe Y, our target property. The pooling of the graph features is also being researched to improve the accuracy of the model. A simple example would be taking the mean of all the vertex features. One of the prime examples of the graph convolution neural network is AlphaFold 2, developed by Google DeepMind and Seoul National University. Predicting the structures of the protein was a 50 years long challenge in the field of biology, which hindered us from understanding the mechanism of protein interactions. The AlphaFold demonstrated the accuracy that rivals the experimental methods, innovating the field of biology. As you can imagine, the convolutional neural network is incredibly complex and is an impressive engineering marvel. Graph convolution is very important in AI chemical science and has shown to be one of the most successful frameworks. And you will certainly work with one if you want to become an AI chemical scientist. I hope this tutorial provided a conceptual overview of the graph convolutional neural network. Happy coding!